Welcome to our lecture online, and here's another interesting phenomenon caused by diffraction of light. And let's say that we have a slit pattern of a great number of slits, thousands and thousands of slits, very, very closely spaced together, so that the distance between them, which is d, is a very small number. For example, let's say we have something that has 2,000 slits scratched in a plastic or glass plate per centimeter. What would be the distance between them? And so the distance would be equal to the inverse of the number of slits per centimeter, or per meter, however you want to write the unit. So in this case, I did it per centimeter. So if we take the inverse of that, that would be the distance in centimeters between any two slits. So in this case, this is equal to 1 over 2,000 per centimeter, which is equal to, if we take the inverse of that, so we had 2,000, then the inverse, and that would be 5 times 10 to the minus 4 centimeters. So that's 5 times 10 to the minus 4 centimeters, which is equal to 5 times 10 to the minus 6 meters, which is 5 micrometers, which means the distance between any two slits is an extremely short distance, small distance of 5 micrometers. When you do that, you form a very interesting diffraction pattern on the screen. Let's say the screen is a certain number of meters away. And it turns out that the angles here are relatively large, not like we see under a normal interference pattern where the angles are very small. With a diffraction pattern like this, the angles are very large. And we no longer talk about the distance from the central maximum. We tend to talk about it in terms of the angle. Where will we find these bright fringes that we're looking for? And in the case that the light that we shine through the slits is 600 nanometers, what will be the angle for the first maximus, we call it? The first max, which is also called the first order. And we'll talk about that in the next video, what that really means. But it's the first bright region found by shining a certain light through a diffraction pattern like that. And so here we can say that the extra distance traveled, which is d sine theta, to find the first maximum, has to equal a full wavelength. That means the extra distance traveled by the ray over here compared to the ray over there is indeed a full wavelength. So we set the extra distance traveled equal to a lambda. They're back in phase, and they then form a maximum or a bright fringe. So set those equal to each other. We get d sine theta is equal to lambda, and therefore the sine theta is equal to lambda over d, and therefore theta is equal to the arc sine of lambda over d. So again, since those are not small angles, we cannot just assume that the sine of theta equals the tangent of theta, because that will not be the case. So plugging in these numbers, we have the arc sine of lambda, which was 600 nanometers. That's 600 times 10 to the minus 9 meters, and divided by d, which we found to be 5 times 10 to the minus 6 meters. So if we take the one divided by the other, let's see, we have 600 e9 minus divided by 5 e to the 6 minus equals, and that gives us the arc sine of 0.12, and if we take the arc sine of that, that gives us 6.9 degrees. So the first maximum is found at an angle of 6.9 degrees away from looking at the central max. So the central max will still be directly across, and the first maximum away from the central max will be found at 6.9 degrees. So where will we find the second maximum? Well, to find the second maximum, the extra distance traveled will be 2 lambda. So this is for the first max, or the first order. To find the second order, the extra distance traveled must therefore equal to be to 2 lambda, so for the second max. And that means we're going to find, this is, let's call this theta sub 1. To find theta sub 2, we then have to just multiply lambda by 2 lambda. And so we have the arc sine of 2 lambda divided by the distance. And let's see what we get. We get the arc sine of 2 times 600 times 10 to the minus 9 meters divided by 5 times 10 to the minus 6 meters. And see what we get this time. So we get 1200 e9 minus divided by 5 e to the 6 minus equals, and that would be the arc sine of 0.24. So it's equal to the arc sine of 0.24. And when we take the arc sine of that, we get 13.9 degrees. And that would be, of course, for the second maximum. Now you can see how that is definitely limited, because eventually we're going to get up to the arc sine of a number that's greater than 1. Of course, you can't find the arc sine of that, which means the angle is so large you no longer see a bright fringe. So the next one will occur when we have 3 lambda. That means the arc sine of 0.36. So to find theta sub 3, we need to find the arc sine of 3 lambda divided by d, which will be 0.36. And of course, 0.36, take the arc sine of that, we get 21.1 degrees. Then to find theta sub 4, that's equal to the arc sine of 4 lambda divided by d, and 4 lambda divided by d will be the arc sine of 0.48, so 0.48, take the arc sine of that, that would be 28.7 degrees. And then to find the fifth one, that's equal to the arc sine of 5 lambda divided by d, which is 0.60. And you see we're getting to the limit there, so 0.6, take the arc sine of that, that's 36.9 degrees. And you can also see how the separation of the angles begins to increase as we get closer and closer. Theta sub 6 is equal to the arc sine of 6 lambda, that would be 0.72, and 0.72, take the arc sine of that, that would be 46.1 degree. Then theta sub 7 is equal to the arc sine of, that now would be 7 lambda divided by d, that would be 0.84. Take the arc sine of that, take it again, 0.84, arc sine, that would be 57.1 degrees. And finally, theta sub 8 is equal to the arc sine of 8 lambda over d, which would be 0.96. That would be 73.7 degrees. And that's it. If we try to find the very next bright spot, you're not going to find them. So in this case, you will find 8 bright spots on either side of the central maximum. And anything beyond that, the angle is so large that you'll no longer see it. So you can see that there's a very spread out pattern that you get by having a diffraction grating like this. The advantage of that is that that allows light to be split up under a great number of, over a wide angle, and so you can see very tiny differences in the wavelengths that way. So in our next example, we're going to see how we can very usefully use, in a useful manner I should say, use a diffraction grating to separate light waves of slightly different wavelengths to be able to measure their wavelengths very accurately using this apparatus. But anyway, again, going to the technique, the extra distance traveled by 2 adjacent waves is always going to be d sine theta. We're always going to set equal to lambda, 2 lambda, 3 lambda, 4 lambda, 5 lambda to find the subsequent bright regions. In some cases, there's only very few before you run out of room, before the angles become so big you can no longer take the arc sine. And that is how you find the diffraction grating pattern of a diffraction grating.